What if we could build a star on Earth? A power source that never runs out, creates no carbon emissions, and uses fuel from seawater. It sounds impossible, but this is the real promise of nuclear fusion. And today, we're diving into why it's so unbelievably hard to make it work. For decades, scientists and engineers have been chasing this dream, trying to build a star on Earth. But if the concept is so simple, why is it so incredibly hard to achieve? And why, despite the immense challenges, do we keep pouring billions of dollars and countless hours of brain power into this quest? Today, we're diving deep into the fascinating, frustrating, and ultimately hopeful world of nuclear fusion. So, what exactly is nuclear fusion? At its core, it's the opposite of nuclear fission, which is what powers our current nuclear plants. Fission splits heavy atoms like uranium to release energy. Fusion, on the other hand, smashes light atoms together, like isotopes of hydrogen called deuterium and tritium, to form a heavier atom, helium. In this process, a tiny amount of mass is converted into a huge amount of energy, thanks to Einstein's famous equation, E equals mc squared. The sun does this effortlessly. Its immense gravity crushes hydrogen atoms together at its core, where temperatures reach a blistering 15 million degrees Celsius. Recreating that process here on Earth, without the benefit of a star's gravity, is where the real trouble begins. To get atoms to fuse, you need to overcome a fundamental force of nature, the electrostatic repulsion between them. Atomic nuclei are positively charged, and like magnets with the same poles, they desperately want to push each other away. To force them together, you need to create some truly extreme conditions. We're talking about temperatures over 100 million degrees Celsius. That's more than 6 times hotter than the core of the sun. At these temperatures, matter turns into a fourth state called plasma, a superheated, electrically charged gas. No physical material on Earth can contain something this hot. If this plasma touched the walls of its container, it would instantly cool down, stop the diffusion reaction, and likely destroy the container itself. So, how do scientists solve this hot potato problem? They use magnets, really, really powerful magnets. The most common design for a fusion reactor is called a tokamak, a Russian acronym that essentially means toroidal chamber with magnetic coils. Picture a giant, hollow donut. Inside this donut, immensely powerful magnetic fields are generated to trap and suspend the scorching hot plasma, keeping it from touching the walls. These magnetic fields act like an invisible bottle, squeezing and shaping the plasma, allowing it to reach the insane temperatures and pressures needed for fusion. This concept is called magnetic confinement, and it's the leading approach in the global race for fusion energy. Building and controlling these magnetic cages is an engineering marvel, requiring some of the world's strongest superconducting magnets cooled to near absolute zero, just meters away from a 100 million degree plasma. The contrast is mind-boggling. But even if you can heat the plasma and contain it, you face another massive hurdle known as the Lawson Criterion. This is a rule of thumb in fusion research that defines the 3 conditions you need to hit simultaneously to get a self-sustaining reaction. First, you need high enough temperature, which we've talked about. Second, you need sufficient plasma density. You have to pack enough fuel particles into the space. And third, you need a long enough confinement time. You have to hold it all together long enough for the fusion reactions to actually happen and produce more energy than you're putting in to heat the system. Think of it like trying to light a fire with damp wood. You need enough heat, enough wood packed together, and you need to hold the flame there long enough to dry the wood and get it to catch. Getting just one of these conditions is hard. Getting all 3 at the same time is the grand challenge that has occupied physicists for over 70 years. For a long time, the joke in the physics community was that fusion is always 30 years away. But recently, something shifted. We're seeing real, tangible breakthroughs. In late 2022, the National Ignition Facility in the US achieved a major milestone. Using a different approach called inertial confinement, which uses powerful lasers to implode a tiny fuel pellet, they achieved ignition. For the first time in history, a fusion reaction produced more energy than the energy delivered to the target. This was a monumental proof of concept, showing that the physics works. Meanwhile, massive international collaborations like ITER, being built in France, are pushing the boundaries of magnetic confinement. ITER is designed to be the first fusion device to produce a net energy gain on a large scale, 10 times more energy out than in. It's one of the most complex science projects in human history, a joint effort by 35 nations. These breakthroughs are turning 30 years away into a tangible and much closer reality. So, why does all this matter? Why go through all this trouble? The answer is simple. Our future may depend on it. Our world is hungry for energy, and that demand is only growing. At the same time, we're facing the urgent crisis of climate change, driven by burning fossil fuels. Fusion offers a clean, safe, and virtually limitless energy source. The primary fuel, deuterium, can be extracted from ordinary seawater, and there's enough of it to power humanity for millions of years. The other fuel, tritium, can be produced inside the reactor itself from lithium. Fusion doesn't produce greenhouse gases, and unlike fission, it doesn't create long-lived, high-level radioactive waste. The main byproduct is helium, an inert, harmless gas. Also, a large-scale meltdown like in a fission plant is physically impossible in a fusion reactor. If the confinement is lost, the reaction simply stops. It fails safe. Imagine a future where cities are powered by miniature stars, where energy is abundant and clean, freeing developing nations from energy poverty and reversing the effects of climate change. This is the world that fusion energy promises. It's a world where we're no longer fighting over scarce resources, but are powered by the same clean, sustainable process that makes life on Earth possible in the first place. The path to fusion is long, expensive, and filled with incredible scientific and engineering challenges. It requires us to push the very limits of what we know about materials, physics, and technology. But the potential payoff is nothing short of revolutionary. It's about securing a sustainable future for generations to come. The quest for fusion isn't just a science experiment. It's one of the most important endeavors of our time. And with every new breakthrough, we get one step closer to finally harnessing the power of the stars. Thank you so much for watching. If you found this journey into the world of fusion fascinating, don't forget to hit that like button.